Good afternoon, everybody. Today is, for you guys, January 14th, I think is what it will be. We are doing section 6.3, day 1, properties of trigonometric functions. We've actually, because I did those 3 worksheets kind of ideas, we've actually already discussed much of this information in section 6.1 and section 6.2. I'm just going to kind of go through some of the new stuff, or maybe it'd be slightly written in a different way. Trig function, sine theta. What's the domain? It's kind of saying what kinds of angles can you find the y-coordinate for on the unit circle? Well, you can have any number, and think back to that wrapping function. Any number on that line x equals 1 could wrap onto the unit circle. Same thing for cosine. So the domain is all real numbers for both of those. You can find any number on that vertical line that will wrap onto the unit circle. Range says what kinds of answers can you get out? And if we think about the unit circle, for sine, that's y-coordinates off of the unit circle. Radius is 1. The y-coordinate has to be between -1 and 1. So sine has to give an answer between -1 and 1. Remember, you're giving y-coordinates off of the unit circle. We're going to leave this column blank for a couple of minutes here. Cosine, same idea. You're looking at x-coordinates here. Now, these last 4, these get a little bit tougher. Tangent. What's the domain? What kinds of things can you plug in that you can find an angle for? And because I'm not there, I'm just going to kind of tell you what that domain is and then talk about it. So theta cannot be equal to 2n plus 1 times pi over 2. Where n is a member of the integers. Yikes. That's kind of brutal. And tangent, because it's sine divided by cosine, tangent is undefined when cosine is equal to 0. Cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. Are you seeing the pattern here? It's odd numbers times pi over 2. This expression right here, 2n plus 1, will generate odd numbers. 2 times any number is even, then add 1 makes it odd. So this is odd numbers times pi over 2. Integers allows you to put in positive or negative whole numbers here, or 0. The range off of tangent, when you take a fraction between sine and cosine, or a ratio here, you can get anything. So the range off of tangent is all real numbers. Cotangent, because that's cosine over sine, anywhere where sine is equal to 0 is going to make cotangent undefined. And sine is equal to 0, at pi, at 2 pi, at 3 pi, at 4 pi. So integer values of pi. So theta cannot be equal to n times pi, where n is an integer. The range off of cotangent, just like tangent, when you compare 2 numbers, you can get any value, fraction there. Secant is 1 over cosine, so it's going to be like tangent in terms of its domain, because the denominator of cosine cannot equal 0. So the domain here is theta cannot be equal to 2n plus 1 times pi over 2, where n is a member of the integers. Cosecant, The domain here is going to be like cotangent because the denominator of sine cannot be equal to 0. So theta cannot be equal to n times pi. N is a member of the integers. Yes, you have to write n as a member of the integers every time. All right, domain for these two, it's going to be the same. If we look at just secant, that's 1 over cosine. Cosine is a number that's in between -1 and 1. And if you take the reciprocal of the numbers that are between -1 and 1, you get anything between negative infinity up to -1 inclusive, or 1 to infinity, including the 1. Cosecant, same range. All right, now period of a function. The period of a function tells how often the y values of a function repeat each other, or repeat themselves. Again, the period of a function is how often the y values of a function repeat themselves. That definition is a very informal definition. I'm going to give you a formal definition here in a couple minutes. The shortest period is called the fundamental period. Shortest period is called the fundamental period. All right, so let's go back and let's talk sine and cosine here for a minute. Sine and cosine are going to repeat themselves every 2 pi, every 4 pi, every 6 pi, every 8 pi. So one time around is 2 pi, and then during the second time around we start repeating those values again. Third time around, repeat those values again. So sine and cosine repeat themselves every 2 pi, every 4 pi, every 8 pi, etc. So the fundamental period, the shortest one up there, is 2 pi. And that's what's going to go up into this column up here. Fundamental period is the shortest period that the things repeat themselves. Sine, 2 pi. Cosine, 2 pi. Secant, because that's the reciprocal of cosine, it's going to repeat itself the same length, 2 pi, as is cosecant, also 2 pi. Tangent and cotangent, they're different. Tangent is positive here, tangent's negative here, tangent's back positive over here because, oops, I gotta move over and make sure you can see it, because both the x and the y are negative, and again back to positive. Tangent and cotangent repeat themselves every pi. So this value right there, the relationship between x and y, is going to be the same as right over here, the relationship between x and y. Is the x the same as the x here? No. Is the y the same as the y here? No. but the fraction y over x is the same value as the fraction y over x over here, because the negatives cancel each other out. Okay, now the formal definition says the following. A function is periodic if f of theta plus p is equal to f of theta, where p is the period and the smallest possible value of p is the fundamental period. So if we just think about this, this says the function value at an angle is the same as the function value at theta, that angle plus whatever that period is. And if we apply it to a specific example, look down here at cosine 420. We're in degrees now, so think degrees for a moment. For cosine, the period was 2 pi radians, or 360 degrees. That says that you can write this at this 420 as the cosine of 360 degrees plus 60 degrees. There's the angle then, and there's the period P. So that says this is the same as cosine of 60, which is a half. Personally, I think that's a lot of writing to do, and a lot of, I think it's harder to actually separate out those periods. That's why I like doing these with the wrapping function, because if we go back to this cosecant of 450, we'll just think, where is 450? 360 gets you around once, and you have a remaining 90 to get here. So I'm looking for 1 over the sine of 90. Sine up here is 1. 1 over 1 is 1. We've been doing this period part, this fundamental period, by just wrapping around the circle continually. Let's just take a look at this one, the tangent of 9 pi over 4. When you have things that are larger than 2 pi in here, then change that to a mixed number. So that would be 2 1/4 times pi. Two pi gets you one way around, then I have a remaining pi over 4 right there. Tangent there, sine over cosine, that's 1. 25 pi over 6, that is 4 1/6 pi. 4 pi gets you one time around. Oh, I lied. 2 pi gets you one time around. 4 pi gets you the second time around. Pi over 6 sits right there. Secant, that's 1 over cosine. Cosine here is square root 3 over 2. So 2 divided by the square root of 3 is the secant. And then let's rationalize that. 2 square root 3 over 3. Okay, so again, here's how you can write it out using the period, or you can just continue to wrap as we've been doing over the past several days. This one down here, you do have to recognize that this is a periodic function notation. Tangent of theta is equal to 3. Find tangent theta plus tangent of theta plus pi plus tangent of theta plus 2 pi. Well, recall that the period of tangent is pi. So, well, I know this one, the tangent of theta is 3, plus, this one's the angle plus the period. That's the same thing as tangent theta. That's a 3. This one, you're adding on 2 of those fundamental periods. That's also tangent theta, which is also a 3. So we end up with 9. Okay, now, again, remember when I started this section a couple of minutes ago, I said that a lot of this stuff in this section, section 6.3, we've done before. So we're just kind of go back and pick up little more bits and pieces. And here's one of these pieces. Sine theta is -3/5, and theta is in quadrant 4. Find the values of the other 5 trig functions. These 2 examples are very similar. I showed you 2 ways to do this in class on Tuesday. I'm going to do one of them one way and one of them the other way. You can do them whatever makes you happiest. One of the ways to handle this is to use just plain old x, y, r. And we remember that sine is y over r. Y is -3, r, 5. Remember, r has to be positive. That means that the y has to take on the -3. And then we need to figure out this x value. Well, we know x squared plus y squared equals r squared. X squared plus 9 is 25. Or if you recognize this triple, this is a 3, 4, 5. You do need to verify theta is in quadrant 4. In quadrant 4, x is positive. So this does have to be a positive 4. Had I told you that theta was in quadrant 3, then you would have made x be a -4. Once you have this set up, then you can just go ahead and the other 5 trig functions. So cosine theta, x over r. Sine theta we already know. Tangent theta is y over x, -3 over 4. Secant theta is the reciprocal of cosine, so that's 5 over 4. Cosecant theta, the reciprocal of sine, and we know sine right here, that's -5 over 3. And cotangent theta, reciprocal of tangent, -4 over 3. Okay, so that's one way to handle those, just writing out x, y, and r. Another way to handle this, and some of you may like this way better, is to draw a right triangle and take a look at what's going on here with the right triangles. First thing I want to look at here is cosecant theta is equal to 3. That means 1 over sine theta is equal to 3, which means sine theta is 1/3. Now we can go through and draw this. All right, sine is, we need to draw this. Ooh, sine's positive. That could be first quadrant or second quadrant. Right now I don't know which one to draw, so I'm going to look at my next piece of information. Cotangent is negative. That's cosine over sine, negative. Well, you know the sine is positive. That means the cosine has to be negative, right? Because sine is 1/3. So sine's positive, which means the cosine has to be negative, which means we have to be in the second quadrant. Second or third for cosine to be negative, but we know sine's positive, so it has to be in the second quadrant. It doesn't matter where I draw this. I'm just going to put it up over here. Here's the angle. There's theta. Excuse me. All right, create your triangle. So we're going to drop a vertical to the x-axis. And we know this is what you're going to use as the angle for the triangle, right there. And sine is 1 over 3. So sine is opposite over hypotenuse. So this is 1. That's 3. You're going to have to use Pythagorean theorem to get this side down here. This side squared, 9, minus that side squared, minus a 1, that's 8. Square root 2 square root 2. But then think we're going to the left, so that has to be negative. Once you have that information, then we can just start writing the answers here. Cosine theta, adjacent over hypotenuse, so negative 2 square root 2 over 3. Sine theta, we figured out a couple of minutes ago. Tangent theta, opposite over adjacent. So that's going to be 1 over a negative 2 square root 2. If I rationalize, that's going to give me square root 2 over 4, but it's negative. Secant theta, flip cosine over, 3 over 2 square root 2. I'm not losing my negative here. Rationalize, and we're going to get negative 3 over, negative 3 square root 2 over 4. I'm running out of space here. Cosecant theta we already have in the problem. One more, cotangent theta. All right, don't flip over your answer for tangent, because then you're going to have to rationalize the denominator. Why don't we take this original fraction right here, negative 1 over negative 2 square root 2, flip that one over, negative 2 square root 2. Perfect. Thank you very much. Here's end day 1. We will continue tomorrow on Friday. Thank you very much. Have a good evening. Bye now.